It is the 9th of September, 2025, approximately 7:55 a.m. Today we're going to be getting, well, for this, we are going to be getting into the Chapter 2 exercises for algorithm analysis out of the CLRS tome. We're going to be getting into the exercises here, so we'll start with one, which is, well, we'll start with what we're doing is Chapter 2. We've already been through Chapter 1's exercises and the single problem that was provided in the book. Now, we're moving on to Chapter 2, as I said earlier, so we'll be working on that. Oh boy. Okay. So, it tells us use figure 2.2 as a model. Illustrate the operation of insertion sort on an array initially containing the sequence (31, 41, 59, 26, 41, 58. So, intuitively, well, what's the intuition for this? What's the intuition for going and solving this? Well, treat the left prefix as your stored hand. As your sorted hand. Well, okay. I gotta show you figure 2.2. Because if I don't show you figure 2.2, well, it's in the book, you can look at it, but if I don't show you figure 2.2, then really, you're not gonna really get the intuition of it all. So let me just kind of, there it is. All right. Now, proceeds along these steps, right? A through F it does. And so treat the left prefix as your sorted hand. At step J, pull out the key, the array A of J is the best I could say it, like this indice J, I guess you could say, of A. Slide any larger elements in the prefix 1 position right, and drop the key in the hole that opens, right? So let's look at this a bit more rigorously to the example of figure 2.2. Okay, so let the outer loop index be J is equal to 2 all the way up to 6, and the key be A, open bracket J, close bracket, at each step. So what they did in figure was to sort, this is going back to the figure. What they did is to sort the figure such that we had 5, 2, 4, 6, 1, 3, It's from figure 2.2. And so this was the initial. J equals 2. Oh, let's be a bit more precise about this. So J equals 2, key equals 2. What does that get us here? Well, we have 5, 2, 4, 6, 1, 3, which implies, and then we have 2 here, right? 5 here. Now, let the outer loop index be 2 all the way through 6, and the key be a j, a bracket, open bracket, j, close brackets at each step. So we have 5, 2, 4, 6, 1, 3. Now let's go on and see what this gets us. This gets us 2, 5, 4, 6, 1, 3. Swap places there, right? So, and then we'll continue along this path where j equals 3, key equals 4. What does that get us? Well, from 2, 5, 4, 6. Why do I keep on forgetting the comma? 6, 1, 3. So we've got 5 here, 4 here. Now let's see what's the order of that. Well, 5 is bigger than 4, so 2, 4, 5, 6, 1, 3. So okay, now j is equal to 4, key is equal to 6, right? So what we have here is 2, 4, 5, 6, 1, 3. So we have 6 here. Order appears to be in line. No shifts, right? So 2, 4, 5, 6, 1, 3. That's no shifts. Oh, goodness. Okay, so j is equal to 5, key is equal to 1. So what do we have here? Well, we have 2, 4, 5, 6, 1, 3. So we have like this is where things start to shake up a little bit. We have shift 6, 5, 4, 2 right, and we get 1, 2, 4, 5, 6, 3. Right. So now we have j is equal to 5, key is equal to 1. What do we have? We have 1, 2, 4, 5, 6, 3. 3. So we're going to shift 6, 5, 4 right. One, 2, 3, 4, 5, 6. There we go. Now, what else to say about this? Well, the standard loop invariant holds before processing index j, the prefix a 1 all the way up to j minus 1. Well, a open brackets I all the way up to j minus 1 close brackets is sorted in non-decreasing order. The inner while loop maintains the invariant by shifting all elements greater than key 1 position to the right, and then placing key in the unique position that preserves order. At termination, j is equal to 7. The entire array from a open brackets 1 all the way up to 6 close brackets is sorted. Right, and so we do this sort of thing for this sequence that we're given, right? the sequence that we're given is 31, 41, 59, 26, 41, 58. And if we were to take that all in order, we were to proceed by these steps here. What we get, of course, is the list in order, which would be, 31. What did no? No, that's wrong from the start. Okay. Okay, 26, 31, 41, 41, 58, 59. So you could go along the same sort of progression here, wind up at exactly the same sort of sorted thing here. Do I want to go and do that right now? Let's see. It's kind of organized in the same way, isn't it? Let's see. Is it? Nah, I don't think it is. Okay, so no, it's not organized in the same way. I was gonna say, like, if I could just, say the 1, 3, 6, 4, 2, 5, if that was ordered in that way. Let's see which way it is ordered though, right? So so this would be 1. This would be 1 here because it's that, and then 2, this for funds, right? So that's that, and then 4, and then 5. So that would be the order if we were trying to do it that way. So now it doesn't match any of these, so it'd be its own little unique, not really, because you could find something else that's like this, right? But so basically just look at this and factor it into this line of thinking, okay? And if you go along that reasoning, what you'll get is this sorted sort of thing that I showed you as a result of this here. But kind of want to solve it just for the sake of pedagogy, but I didn't exactly come up with the example right on the spot, which I should have done, but c'est la vie. So it's basically, well, this holds, right? 2, 3, 5, 1, 3, 4. Nothing really changes here. 2, 3, 5. Nothing really changes with that. So for a while, it's not going to change. So 2, 3, 5, 1. Well, then everything would have to shift. Everything over here would have to shift to the right. So what you get is this 1, 2, 3, 5, 3, 4, right? And so we have 1, 2, 3, 5, 3, 4. Well, you'd need to shift everything that's over here. Everything that's, okay, so 3 is over here, so you'd swap places with 5, so you'd get 1, 2, 3, 3, 5, 4. Okay, so you have 1, 2, 3, 3, 5, 4, and then you just swap this one, so you get 1, 2, 3, 3, 4, 5, right? And so there you'd have exactly what we have for the sorted. Convert all of the ones back into the original numbers. 26. You don't have to do the conversion of numbers, of course. It's just how I like to do it because it's a kind of, I guess, isomorphic. Well, what is it? Similar? Roughly equivalent corresponds to the way in which we were doing this more succinctly. So hopefully you can see that. Is that? Yeah. Okay, you can tell what I've written in the corner there. It's just kind of hard to see, but it's up there, enhanced. So that's exercise. That's exercise 2.1-1. Now let's get over to 2.1-2. Okay, so 2.1-2. So for that we have consider the procedure sum array. It compares, it compares, no. It computes the sum of the n numbers in array A open bracket 1 colon n state and loop invariant for this procedure. And use its initialization. Maintenance. And termination properties. Okay, properties. To show, why did I put an E there? I don't know. It's British. No. That the procedure returns the sum of the numbers in A open bracket the array A open bracket colon, A open bracket 1 colon n close bracket. So how would we approach this? Well, let me check the camera first and then, okay, so after I minus 1 steps, the running total is exactly the sum of the first I minus 1 items. Each step adds to the next item, adds the next item. So the invariant slides forward until all items are included. So let's look at a more rigorous, detail-driven solution to that rather than just relying on pure intuition. Okay. So at least, well, at the start of each iteration, with index I such that, well, 1 is less than or equal to I, which is less than or equal to n plus 1, we have that the sum is equal to, well, the summation from k is equal to 1 to I minus 1, and this is on the array A open brackets k close bracket. So initialization that is to say I is equal to 1, right? Our base case in a sense before the first iteration. Sum is equal to 0, which equals the empty sum k is equal to 1, 0 of the array A open bracket k close bracket, which is equal to 0. Now maintenance of this assuming the invariant assuming the invariant holds at the start of iteration I is less than or equal to n, the body executes sum is equal to sum plus A open bracket I close bracket, yielding sum is equal to the summation from k is equal to 1 to I minus 1, array A open bracket k close bracket plus array A open bracket I close bracket, which is equal to sum from k equals 1 to I of the array A open bracket k close bracket, which matches the invariant for the next iteration. Come on. So I'm just going to say what I'm writing here, just in case you can't see, right? So I left arrow, I arrow from right to left, I plus 1. Okay? So it yields the sum that we get here that matches the invariant for the next iteration. Sort of an inductive proof, right? So holds. Now let's see what we can say about the termination. So at termination, the loop ends when I is equal to n plus 1 by the invariant sum is equal to the summation from k is equal to 1 to n of the array A open bracket k close bracket. So the returned value, is the sum of the array A open bracket 1 colon n close bracket. That sort of completes the full thorough look at this algorithm here. Now, state a loop invariant for this procedure. What was the loop invariant, right? Well, the invariant was the base case that we held in initialization. So it's the one that we assume holds at the start of iteration I is less than or greater than n. So we saw that there. We used its initialization, its maintenance, and termination properties to show the procedure returns the sum of the numbers in A from, well, in the array A, open bracket 1 colon n close bracket. So there we go for exercise 2.1-2. Now let's go to exercise 2.1-3. Okay. So for exercise 2.1-3, rewrite the insertion sort. Oh boy. Procedure to sort into monotonically decreasing. Oh, that's cool. Instead of monotonically increasing order. So the goal is to rewrite the insertion sort procedure to sort into monotonically decreasing instead of monotonically increasing order. The only change is the comparison direction. Shift elements that are smaller than the key to the right so that larger elements stay to the left. Right, so very good. Camera check real quick. All right. So how would we look about that? Well, rigorously, the only change is the comparison, right? So how about this? We have decreasing. Well, actually, let's get more room. I already told you what this is about, so I can erase this and proceed to kind of show a bit more pseudocode. So decreasing insertion sort A, comma n, open parentheses, A, comma n, close parentheses, 1 for j is equal to 2 to n, 2, the key, I'm just, saying line by line, open bracket, j, close bracket, key is equal to the array, open bracket, j, close bracket, 3, while, whoops, compilation error, oh, not yet, but I is equal to j minus 1, right? So for while I is greater than or equal to 1, and it's supposed to be just a regular and, but the array A open bracket, I close bracket, is less than the key, which flips the comparison. Five, the array open bracket I plus 1 close bracket is equal to A open bracket I close bracket 6, I is equal to I minus 1, 7, so that's 7 lines, array A open bracket I plus 1 close bracket is equal to the key. So that's the general idea, the pseudocode idea behind how we do this. So just as a sketch to sort of get into the correctness of the thing, right? So doesn't really ask us for this, but let's just go ahead and mention it. The standard loop invariant adapts, right? So at the start of each outer iteration, j, the prefix, a, the prefix array a open bracket 1 to the j minus 1 close bracket is sorted in non-increasing order, right? So non-increasing order. So we have that first. Level the playing field, then the inner loop shifts elements less than key rightward and places the key itself, variable key, value key, I guess. What is it? Places key, yeah, in a unique spot preserving non-increasing order. So sorts it into non-increasing order, right? Inner loop shifts elements less than the key rightward and places key in a unique spot, preserves that non-increasing order, but it also makes it in decreasing order. So that's the sort of correctness sketch of it all. Now that's pretty much it for 2.1-3. Let's move on to 2.1-4. So exercise 2.1-4. For that we have write pseudocode for linear search which scans through the array from beginning to end, looking for X. Using loop invariant, prove that your algorithm is correct. Oopsies. So this time we're actually asked to prove correctness. So what's the sort of intuitive way of going about this, right? So walk left to right. If you see X, return its index. If you finish the walk without seeing it, return nil, right? So let's get into this a bit more rigorously and in detail. So, say we have linear search, right? Linear search, open parentheses A, comma, N, comma, X is the parameters, right? So, let's say line 1 for I is equal to 1 to N. Two, if the array A open bracket I close bracket is equal to X. 3, return I. 4, return nil. Like nihilism, like nothingnessism. But I'm not going to get into talking about nihilism right now. Just, that's an interesting little notation there for something that's nothing in a way. So we have the pseudocode here, right? But what about the loop invariant? So loop invariant, so for the loop invariant, let's see here. At the start of each iteration, with index I being 1 less than or equal to I less than or equal to N plus 1, X does not occur in a open bracket, in the array A open bracket 1 dot 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 I minus 1 close bracket. So for the initialization, for I is equal to 1, the prefix array A, open bracket I mean 1, dot, 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 0, is empty. So invariant holds. Maintenance. Let's check maintenance. Maintenance. Like they're checking your apartment. No. Maintenance. So if the array A, open bracket, I, close bracket, is equal to X, we return I and are correct. If not, then X is not an element of A, of the array A, open bracket, 1, dot, 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 I, close bracket. So at the next iteration, open parentheses, well, at the next iteration, I right to left arrow, I plus 1, the invariant, plus 1, the invariant holds. So now let's see about the termination. Put that up here since I don't like writing down there. So for the termination, if the loop completes, I is equal to n plus 1, and the invariant gives X is not an element of the array A, open bracket, from 1, dot, 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 n. So returning nil is correct. I think nil might mean something different than I thought it was, but I don't know. Because it's like writing null, right? But I mean, it's more specific, context specific. So that does it for exercise 2.1-4. Right? So for exercise 2.1.5, I mean 2.1-5, sorry, consider adding 2 n-bit binary integers A and B stored in arrays these arrays being A open bracket 0 colon n minus 1 close bracket, and the array B open bracket 0 colon n minus 1 close bracket, LSB at index 0. The sum C is equal to A plus B should be stored in an n plus 1 element. Okay, n plus 1 element array C open bracket 0 colon n right add binary integers. Consider adding two n-bit binary integers a plus a and b stored in arrays a and b with their index at 0. Sum C is equal should be stored in a different array. Add binary integers. Okay, so just sort of well, we add bit by bit from least significant to most significant, right? So carrying a 0 divided by 1 as needed, exactly like pencil and paper addition in base 2. So how would we go about showing that in this algorithm? Well, let's take a shot at it. Okay. So we have add binary integers, add hyphen binary hyphen integers, with parameters open parentheses a comma b comma n close parentheses. So for the first line of that, carry equals 0, carrying. So for I is equal to 0 to n is equal n minus 1. For line 2, for line 3, S is equal to the array A open bracket I close bracket plus B open bracket I close bracket plus carry plus what you're carrying, right? So, which is S in the set 0, 1, 2, 3. Is this binary integers? So yeah, so it's like oh wait, so I'll just show you. Okay, so C, so for line 4, we have array C open bracket I close bracket is equal to S mod 2. Oh yeah, for a moment I was like, well, how do I explain modular arithmetic? And it's like, well, they already know modular arithmetic. If you're like looking at algorithm analysis, I mean, you would have had to have seen modular arithmetic by now, but basically it's like, say you have like 3 mod 2, well, the answer would just be 1. It's like what remains after you divide the thing by 2, right? So that's sort of the basics of what this thing means, and we need that because, again, binary, so we're going to be getting 1 or 0, right? So going on to line 5 here, carry is equal to the floor function is equal to floor of open parentheses S divided by 2. 6, whoopsies. This is now outside of the for loop. We have the arrays C open bracket N close bracket is equal to carry. And that does it for, oh wait, yeah. So this helps ensure, this line 5 here, that ensures it's 0 or 1, right? So that's why we have that floor function. So, I mean, but, yeah, we need it, but it's like at the same time, yeah, we need it, yeah. I was gonna say, it's like mod 2, if you do things mod 2, it kind of guarantees that you're gonna have either 1 or 0, but if you have the floor function, but it doesn't involve carry, right? So you need carry here. It needs to be here into the carry function. I mean into the carry variable. And so line 6 can use that. So array C open bracket and close bracket is equal to carry. So return. So it's just somebody named Carrie. They're just gonna be like, what? No, but line 7 return. Return C. Right, so let's think about what this means in terms of correctness. So where would I put this? I'll put this over here. Just kind of like hollow this thing out. So have we done what we were asked to do? Yes. So let's just look at the correctness anyhow, right? So correctness, after processing bit I minus 1, i.e. at loop index I, we have the summation, okay, how do I say this? Summation k, from k equals 0 to I minus 1 of the arrays C open bracket k close bracket times 2 to the k plus carry times 2 to the I is equal to the summation k is equal to 0 to I minus 1 of the array A open bracket k close bracket times 2 to the k, which, you know, I should say, how should I say this? Is it, yeah, okay. Because I'm thinking about like the parentheses. If I'm wrong with like the parenthesization, then by all means correct me. But for now, it's just like, well, plus the summation k is equal to 0 to I minus 1 b, I mean the array b open bracket k close bracket times 2k. Initialization holds with all sums. Zero. This is what we want. It's our base case, right? So initialization holds there. How about maintenance? Maintenance follows, whoops, it's kind of like a, maintenance follows from base to addition such that S is equal to array A open bracket I close bracket plus B open bracket I close bracket plus carry writes the array C open bracket I close bracket is equal to S mod 2 and updates carry is equal to the floor function S divided by 2, preserving, maintenance is always going to be the longest part of any correctness proof, preserving the weighted, well, not always, I imagine there's probably an example out there, right? Weighted sum identity. Okay, let's move this over here so that we don't have to write down there. Termination. Well, let's say at termination, I is equal to N. Carry is stored as the array C, open bracket, N, close bracket. So C encodes A plus B in binary. So we have the correctness sort of laid out there, even though we didn't really need that for this exercise. It's a good thing to have. It's good practice. So, yeah. Trying to check how much we have left. Quite a bit. That's fine. You can get it off soon. Let's do one more for now. Check the camera. Camera's good. So for the first exercise of section 2.2, 2.2-1, since that was the, check just to be sure, good, okay. Well, for this, we have express the function n cubed divided by 1,000 plus 100n squared minus 100n plus 3 in terms of theta notation. So for large n, the highest degree term wins, right? That's the best way of saying it. What is it? Dominates? I guess dominates makes more sense, right? Cubic beats quadratic and linear, right? So the function grows like n cubed. So to put this more rigorously, there exists C1, C2 greater than 0, and n naught such that for all n is greater than or equal to n naught, C sub 1 times n cubed is less than or equal to n cubed over 1,000 plus 100 n squared minus 100 n plus 3, yeah, which is less than or equal to C sub 2 times n cubed. Now, for example, take n naught to equal 1,000, C1 to equal 1 over 2,000, and C2 to equal 1 over 1,000 plus 100 over n naught plus 3 over n naught cubed. So this isn't too thorough. It's not like a proof thing, but we can express it such that we have n cubed divided by 1,000 plus 100n squared minus 100n plus 3 is contained within the set of functions theta of n cubed. I think that completes what it's asking for. If it's not, again, like, correct me. I would rather be right than right and humble than wrong and prideful. Yeah. Okay. And that is it for now.